Human problem solving is deeply intuitive. We skip steps, we make assumptions, we rely on context. But computers operate differently. A microchip is entirely deterministic. It only does exactly what it is told, in the exact order it is told to do it. Bridging the gap between our fluid intuition and that rigid machine execution requires an intermediate step. Before writing a single line of code, software engineers use a universal logical architecture to map out the problem, completely decoupled from the quirks of any specific programming language. This animated diagram shows the basic vocabulary of that architecture. Whether we are drawing visual flowcharts or writing plain English pseudocode, we rely on 4 geometric primitives. Ovals set the boundaries. They mark the exact start and end points of a sequence. Parallelograms handle the data crossing those boundaries, defining what information comes in and what gets printed out. The actual computation happens in the remaining 2 shapes. Rectangles execute internal processes, like mathematical calculations. Diamonds execute conditional logic, asking a question and splitting the path based on the answer. Every complex software system on Earth, from a simple calculator to a global search engine, is constructed from just 3 patterns of control flow using these basic shapes: sequence, branching, and iteration. The absolute baseline of computing is sequential execution, defining a state and transforming it linearly, step by step. We can map out a simple operation to demonstrate this, like adding 2 numbers together. This flowchart builds that linear sequence. We initialize the program and then immediately define our known inputs. Here, we request 2 unknown variables, a and b. The data then drops into a process block. This is a discrete mathematical operation. The system creates a new variable, sum, and stores the combined value of a and b inside it. The new state is complete, so we output the value of the sum to the user and terminate the sequence. This visual stack translates directly into text-based pseudocode. We define our inputs, calculate the sum, print the result, and exit. It reads like a recipe. In pure sequential execution, the data state is rigidly defined, transformed exactly once, and outputted. There is no variance, and the execution path never changes. Linear sequences are predictable, but they are completely blind. They cannot adapt to changing data or make intelligent decisions based on what they process. To build logic that reacts, we use conditional branching. This diagram shows a diamond decision block asking a simple question. Is an unknown number, n, even or odd? To find out, we rely on a programmatic tool called the modulo operator, represented by a %sign. Instead of dividing 2 numbers and giving you the quotient, modulo divides the numbers and returns the remainder. We divide n by 2 and check if that remainder is 0. Notice the double equal sign. In programming, a single equals assigns a value to a variable. A double equals is a Boolean equivalence check. It is asking if the statement is true or false. If the check evaluates to true, meaning the remainder is 0, the algorithm branches down a path that outputs an even result. If the statement is false, the remainder is not 0. The execution branches down an entirely separate path to output odd. In text-based pseudocode, this visual fork maps strictly to an if-else control structure. If the condition is met, run the first block of code. Else, run the second block. By introducing a simple Boolean check, a single static algorithm can handle infinitely varied inputs, dynamically routing the data to the correct outcome. Branching allows for decisions, but there is still a massive computational hurdle. What if you need to perform an operation a scalable number of times? Say, summing every number from 1 to n. You cannot manually write 1,000 sequential steps. This flowchart models iteration. First, we establish our baseline variable states in memory before any action occurs. We initialize a starting sum of 0 and a counter starting at 1. The engine of this iteration is a decision block. It evaluates a specific threshold to determine if the process should continue. Here, we ask if our current count is less than or equal to our target number, n. If true, we update our state. We take our current sum, add the current count to it, and store that new, larger total back into the sum variable. Then we execute a critical safety step. We increment our counter variable by 1. Without this exact step, the count would always be 1, the condition would always be true, and the program would crash in an infinite loop. Finally, the control flow routes backwards upon itself, landing right back above the initial decision block to evaluate the new count. This cyclical architecture is known in pseudocode as a while loop. It guarantees that the mathematical condition is reevaluated before every single cycle. This feedback loop is what gives software its massive scale. It allows finite code to execute thousands or millions of operations automatically. We can combine sequence, branching, and iteration to solve highly complex problems, like verifying if a given number is prime. This requires initialization, looping, and internal branching to all work in concert. The mathematical constraints here are straightforward. A prime number is only divisible by 1 and itself. So we systematically divide our target number, n, by an incrementing divisor, let's call it I, starting at 2 and climbing up to n-1. This split-screen diagram tracks our logic on the left and our memory states on the right. Engineers use a manual process called a dry run, tracking how variables mutate over time. For this test, n is 5 and I starts at 2. On the first pass, we check if 5 modulo 2 equals 0. It doesn't. So the system branches down the no path, increments our divisor, and our memory table ticks I up to 3. The loop fires again. 5 modulo 3 is not 0. I becomes 4. 5 modulo 4 is not 0. I becomes 5. Now our initial loop constraint that I must be less than n evaluates to false. Because the loop constraint was broken, the iteration safely terminates. It drops down the final path to print our output. 5 is a prime number. Notice the efficiency of the internal conditional break. If we tested the number 6, the very first modulo check against 2 would evaluate to true. The system would instantly break out of the loop, print non-prime, and save the processor from running useless calculations. Executing a methodical dry run ensures this exact integrity. It proves the logic handles dynamic memory states correctly before an engineer ever touches a keyboard. Flowcharts and pseudocode map the logic flawlessly, but they are entirely theoretical. You cannot feed an English sentence or a geometry diagram into a CPU. To make it run, that theoretical logic must be translated into formal, strict syntax using a language like C++, written inside a digital editor. Computer hardware is blind to language. A processor only comprehends electrical currents, a high-voltage state for 1 and a low-voltage state for 0. This animated schematic introduces the tool that bridges the gap. A compiler acts as the ultimate mechanical translator between human-readable syntax and hardware physics. The compiler strips away the C++ formatting and converts your precise logic directly into an executable payload of pure binary instructions. Mastering the visual abstraction of control flow guarantees robust problem-solving power. Once the architecture is mathematically sound, the translation into silicon is inevitable.